Okay, good morning everyone, and thank you very much for the invitation to give a talk here to a topic that is somehow new to me, but it's also very old to me, as I will later explain to you. Okay, so I will talk about the challenges of AI and machine learning in educational data analysis, and particularly talk about the challenges with regard to understanding what we are doing here and also explaining where I think some AI is not yet as good as humans are, but it might change, of course, in the future. Okay, so AI and machine learning is, of course, not new. There were major developments in the 1950s. Just think about Alan Turing and the Turing machines. But there were additional waves in the 80s and 90s. And in the 90s, I studied computational statistics in Vienna. And I already programmed there genetic algorithms, neural networks. But it was clear to everyone we cannot apply those methods because we lack the data and we lack the computational capacities. So we had the methods. It was very exciting to program these things, but we realized it was not really applicable in applied research. However, this changed now, right? What changed? Now we have massive data sets available, which I refer to as big data. Then we have powerful computational infrastructures available. And now we have much more advanced AI and machine learning methods that are nowadays already applied and will further advance in future. However, the question is, what are the implications for science and research? Will be there a shift in the epistemic goals of science and research? And that's the question I'm trying to address here. Do we shift from a causal explanation and understanding to a correlation and prediction-based decision-making? And understanding is no longer that important. So to clarify a little bit of terminology, when I say theory, I mean it in a very broad sense. It includes global, local, contextualized models, laws, concepts, theory elements about how the world works or the data are generated. By AI, ML, also I use a very broad definition. It's everything that is data-driven and an algorithmic system that learn from data to recognize patterns, make predictions, automatize reasoning or decision making. Realize it's reasoning, it's not understanding. It's not the same, okay? And then big data is also a very complex term. It should be sufficient to say it's more than a lot of data. Right? There are terms in addition to volume like variety, that you have different types of data, veracity, velocity, and so on. These are called the V words, and there are a couple of other V words. And in these days, also particularly in educational sciences, we often use secondary databases, which we try to merge to more focused educational data we collect on our own. Also, I would like to use AI, or I like to think about AI as alien reasoning or alien intelligence, like many philosophers do, because it allows us to differentiate the kind of reasoning by machines that is not understandable or relatable to human thinking or reasoning. So it's better to think about it something completely different with its own value and its own advantages we just might not fully understand. Okay? Okay, so now I ask ChatGPT what educational research is about. Okay, what are we doing here, right? And I was very relieved to see that our alien intelligence still values or says it's about improving educational theory, right? And practice by generating knowledge for informed decision making, right? And then it says that we use structured methodologies and we solve problems, improve practices, and it's about understanding educational phenomena, right? So AI still thinks understanding is important, and I'm relieved to see this. And it's also about a meaningful interpretation of results from quantitative data analysis. So But there are, particularly in the computer sciences and also statisticians, proclaim the end of theory in science. And there was already in 2008 an article by Anderson in the Wired magazine, and he said, the end of theory. The data deluge makes the scientific method obsolete. Or in another article, alien knowledge, when machines justify knowledge. Or alien reasoning is a major change in scientific research underway. Or why an over-reliance on AI-driven modeling is bad for science. Or some even think the reanimation of pseudoscience in machine learning and its ethical repercussions. Right? So there are two different extreme positions on it. One says we no longer need essentially human reasoning, and the other strongly believe in human anthropocentric reasoning. And I classify myself to the latter category, so I will argue in defense of theory and understanding. Okay, so let's look at a few quotes from this famous article by Anderson, The End of Theory, where he says, with enough data, the numbers speak for themselves. Or correlation is enough. We can throw the numbers into the biggest computing clusters the world has ever seen and let statistical algorithms find patterns where science cannot. Or correlation supersedes causation. And this particularly offends me, of course. And science can advance even without coherent models and unified theories. Okay? So there is the belief and fear here that objective alien reasoning replaces human reasoning. And the belief is that data are value-free facts. They speak for themselves. They directly count as evidence, right? And the focus is on correlation and prediction. And it's important that statistical inference, as we know it, no longer plays a role here, only a marginal role, okay? But also that's not new. So one of the godfathers of modern statistics, Carl Pearson, already paved the way for today's AI and machine learning thinking because he valued data-driven methods over theory, and he even thought theorizing is harmful. So he had a very positivist position here. He replaced causation with correlation. He moved causation out of the field of statistics. And he invented and emphasized descriptive curve-fitting regression models guided by only goodness of fitting. Good fit is all we need, right? And that's what we see nowadays in AI and machine learning. Okay, on the other side, we have the proponents of the theory-driven approach and inference, where everything is value-laden and derived from theory, guided by theory. In this situation, nowadays data, of course, neither theory, value-free, nor do they directly represent evidence for phenomena of interest, right? So we need to work hard based on theory to select the data that count as evidence. And there's the claim that without theories and hypotheses, no critical evaluation of inferences is possible, nor is causal understanding of real-world phenomena possible. So in this case, the goal of science and research is about knowledge generation, which means uncovering and understanding, thoroughly understanding real-world phenomena and causal processes. And it's about constructing intelligible causal explanations and theories that can be further used for meaningful interventions in the field, okay? So the question then is, in quantitative research, how do we generate knowledge that allows us first to explain and understand educational phenomena, and second, that allows us to intervene and improve the world through educational practices, okay? And in addition to this, or related to this, we can ask, what is the epistemic role of data and theory in this process? And what is the role of AI and machine learning in this process? And it's very well worth thinking about it because AI and machine learning plays a crucial role nowadays on all steps of the data knowledge generating process, as I will make clear shortly. At the end, I will propose an integrated approach where I try to integrate AI and machine learning with theory-driven model-based research, and I will provide an example where we use local contextualized theory to infer causal effects. So, a short break. So let's discuss the knowledge generating process here. And I use a model by Leonelli, which is an extension of the more famous data model by Patrick Suppis. And she just recently proposed this. And it's an iterative process about how researchers try to explain and understand the world. So on the left-hand side, you see the world, all the real-world processes out there which we humans would like to understand. Right? That what we see on the right side is the knowledge that we would like to extract from the world. And in between, we have objects, data, and data models. They mediate between the real-world processes and our knowledge and understanding. And as you can see here, all the steps are driven by theory. Okay? This would be the ideal as philosophers usually would imagine it. So let's have a closer look at these steps. Objects is essentially anything that may provide evidence for your research question and hypothesis, and in addition, it needs to be transportable, shareable. If you cannot share some objects, and I'll give you an example shortly, with colleagues, then nobody can replicate the findings, right? So it needs to be shared. So think about objects as homework artifacts, pictures or videos, brain scans, blood or saliva samples, tweets, survey item responses at the raw level, or process or log data, right? And those objects are produced through investigative practices, for instance, like tests, questionnaires, game-based learning environments, tutoring systems, or tracking devices, or fMRIs, okay? So once we have the objects, we need to extract or process the evidence, which we then call data. And this is ideally also theory-driven. So data here is a relational category, is clearly context and theory dependent. And what counts as data or evidence depends on who uses them, how, and for which purpose. So how do we obtain the data? And you're all familiar with this if you run some quantitative analysis. It's all about labeling, coding, cleaning, categorizing, classifying, imputing, feature engineering, noise filtering, metadata generation, and so on, you name it. And there are lots of activities out there that we now try to automatize and make it less resource intensive. And in a good way, so if we consider from a philosophical perspective, these activities should be theory aligned with your research question. How you categorize the data, how you label the data, how you impute the data should be driven by your research question, your hypothesis, because you need to generate meaningful evidence that fosters understanding. Okay, so once we have the data, then it's about modeling the data, and we would call this ordering and structuring the data to adequately represent the specific phenomena of interest, phenomena like student achievement or achievement growth, or special causal effects or mediating processes. These are the phenomena we would like to study and learn about. And we use models like measurement models, descriptive or predictive models, causal models, latent growth curve models, mediation models, structure equation models, right, to express the phenomena of interest. However, this is a pretty challenging task because we only get meaningful information out of here if the models adequately represent the phenomena of interest. Okay? Here we can distinguish between substantive adequacy and statistical adequacy. Substantive adequacy means, for instance, if you're interested in mediation, that your mediation structure is aligned with your research question and the hypothesis, that it's substantively correctly represented. So we also need here particularly the alignment of the model with the structural component of the theory, and also some assumptions, particularly causal assumptions, need to be met such that you can attach a meaningful interpretation to the parameter estimates. Statistical adequacy is all about probability theory and the error structure. So it's about correctly specifying the model. Linearity assumption might not be met. You might need to think about nonlinear, non-parametric model. Then you need to think about the error structure, whether you have correlated error terms and how to model it. If substantive adequacy or statistical adequacy is not met, your inference will fail. So we need to take this very serious, and even more seriously in the age of AI and machine learning, as I will later argue. Finally, when we estimated our model, then we can derive knowledge claims about the phenomena of interest. This might be simple visualizations, might be predictions, parameter estimates, causal estimates, and so on. And this knowledge can then be used for causal explanation and understanding, for theory buildings, revisions of theories, for policy recommendations, and so on. So we can actually use the models for doing things in the real world. Okay, so what's the role of AI and machine learning in here? And what we need to do is we just need to put AI and machine learning on top of it and have an influence of the algorithmic procedures at every step of the knowledge generating process. And you all do it already, right? You do it often with theory in alignment with the theory. Sometimes you do it a little bit less with theory and just use the algorithms to make progress, right? Okay, so to just give you an idea for the different steps, what we already do, or might even do more in the future. So in order to generate objects, we use intelligent tutoring systems or game-based learning environments with automatized tracking and logging, natural language processing, and large language models for item generation, questionnaire design, and administration. We use AI-assisted systems for collecting and harvesting network data, for instance, from social media. And of course, that's already heavily used, right? Then at the step of processing the evidence, creating the data, we use supervised and unsupervised learning algorithms like for automatized scoring, feature engineering, noise filtering, and so on. We use also here natural language processing, large language models, deep neural networks, autoencoders, transformers, generative models, and so on and so on. All right? However, the question is here, when we automatize these procedures, do the processed data count as evidence for your research question? And that's a very important question we always need to ask ourselves and not take it for granted. Okay? Then at the step of representing the phenomena for curve fitting, prediction, or variable selection, we have the lasso, decision trees, random forest, support vector machines, deep learning, double debiased machine learning, causal forests, meta-learners, causal discovery algorithms, and that's probably only 1% of the methods that are already out there. Okay? But also here, when we use those automatized models, do they actually adequately represent the phenomena of interest? If they fail to do so, the question is, what can we actually learn from these models? Okay. And finally, once we have the output of our analytic procedures, we of course use AI and machine learning, mostly AI here, for basic explanations and interpretations or report writing, right? Or to make sense of complex predictive models and their corresponding parameter estimates. There are AI tools like shapely additive explanations or local interpretable model agnostic explanations. And these tools are, for instance, heavily used in credit scoring and then business applications. So they use these tools to make sense of the data, right? And then do first the credit scoring, and then you all get some credit scores. Okay, so if we would believe in a theory-free or theory-agnostic ideal, right, we will cut all the ties to theory here, and there might be only a weak link between theory and knowledge, but if we do so, the question is, what do we actually learn here? What is the result we obtain here good for? And how can we use it to intervene, to improve the world? However, in this world, so model agnosticism is considered as a desirable feature because it's automatized knowledge generation or alien objective reasoning, and it replaces on the fallible human subjective reasoning. Right? So that's one of the claims. That's why often it's seen as an advantage. But the question is, can it work? And if it works under certain circumstances, when does it work and what are the limitations? Okay, so now I talk a little bit about not the challenges of AI and machine learning, what the problems are, and only addressing a few more general aspects here. And I will talk about epistemic opacity, theory-agnostic heuristics, unknown finite sample properties, the negligence of statistical adequacy, unknown error probabilities, arbitrariness of correlations. But there are many other particularly model-specific issues, and not all these issues apply to all the approaches to the same extent, but it gives you a good idea what the conditions are, what might prevent us from learning from AI or machine learning. One important aspect is these issues are listed here. They can be avoided with traditional statistical approaches if you take them serious. But if you wouldn't take them serious, you can easily replace it with AI and machine learning, right? And I will get back to this a little bit later. So there are two aspects of opacity. Opacity of the algorithmic process that produces the output. And the problem is that it becomes a black box, and we no longer understand what's going on inside the black box. And Humphreys essentially said, so the epistemically relevant elements we would need to understand what's going on are often unknown. So we are left in the dark. We only see the input, we see the output. And the difficulty is making sense of the output. There's a second type of opacity, which is about the opacity with respect to the phenomena being studied, because it's often unclear whether the process data count as evidence, as I already mentioned. And it's often unclear whether the AI ML models adequately represent the phenomena of interest, right? So overall, it's unclear whether the results actually support the causal explanation and understanding, and how we can actually use this information for educational practice. And my claim is that an unwarranted ad hoc explanation and decision making that is not based on theory often results in results of questionable validity and reliability. So the second aspect is the theory-agnostic heuristics. Almost all AI and machine learning methods are built on objective functions, loss functions, and they are used in order to optimize the fit, to get, let's say, a perfect fit on the curve, perfect classification. However, these objective functions are usually chosen based on mathematical considerations and computational efficiency rather than theoretical and data considerations. So they're completely disconnected what their research is about and what the data structure might look like, right? In addition to the objective function, we have lots of other structural and procedural aspects of the model architecture. Think about the number and type of layers in a neural network. Think about the depth and the splitting rules in a tree. Think about tuning parameters like penalty terms in the lasso, right? Those are usually determined without theory, and it's inverse when you use the default settings. There is no guarantee that the default setting will be aligned with what the data structure looks like. And the problem is when you choose objective functions, the structural and procedural tuning parameters, they superimpose their own structure on the data. So what you might then see is not necessarily what the data speak for themselves. The algorithm starts talking, because you will see the structure of the algorithm, not of the data. So they might fail to produce the adequate evidence and correctly represent the phenomena of interest if not carefully used. So then another issue is that AI and machine learning works very well if the number of observations goes to infinity, and if the number of variables is huge. Not for all methods, But for most methods, in addition, we always have something called these mild regularity conditions or smoothness conditions that need to be met in addition, because if all these assumptions, large data, infinite data, large set of variables, and the conditions are met, then those methods might meet the oracle property, meaning they will tell you the truth about the data generating process. And you can formally prove those aspects sometimes. However, in practice, we face finite data. We don't have infinite large data sets. We also have often only a few hundred of covariates, right? You might think that's a lot of covariates, not for machine learning or AI, right? And there's a famous quote by Lucam, already put forward in 1986, who says, limit theorems, which means as n tends to infinity, are logically devoid of content about what happens at any particular n. So we are often not sure how good the methods work with the finite data set. By finite, I mean when you have even 10,000, 20,000, 30,000 observations, you might still be in troubles. Okay? The issue is the slow convergence, because the algorithms have a very poor convergence behavior, so the results might be considerably biased even with 10,000 observations, and standard errors, even if they deliver standard errors, most of the methods do not even provide standard errors anymore, may be large. Right? So we do not learn a lot with finite data. Then another aspect is the negligence of statistical adequacy, because everything is built on goodness and fit, but they fail to provide testable probabilistic assumptions and controllable error probabilities, like a good old regression models, right? We know the type 1 error rates and type 2 error rates, distribution essentially, and we also have testable probabilistic assumptions. Think about residual diagnostics. You can carefully check whether your model is statistically adequate. That's gone with machine learning, right? So it's hard for the validity and reliability to assess, and it's very important to realize excellent goodness of fit is neither necessary nor sufficient, particularly in causal inference. Causal inference, goodness of fit is not important. You will see later what's important in causal inference, okay? So AI and machine learning models are, if they are statistically inadequate, then the parameter estimates and correlations neither warrant an inferential nor causal interpretation, and they are of little value for causal explanation and understanding. So another issue is, I think I skipped this. I have 15 minutes left about, so I will skip this slide, although it's a very interesting one, but it's a little bit more technical. But let's talk about the arbitrariness of correlations. So when we use AI or machine learning, then we get usually lots of parameter estimates and correlations, but they are typically unrelated to theory and research questions, right? And thus meaningless, because they might be contaminated with lots of confounding, right? It's a correlation, but what are we doing with the correlational association? You would like, I hope so, to causally interpret correlational measures, right? In order to understand how the world produces some outputs when you start changing the input. So with big data and even with multiple AI and machine learning steps along the entire knowledge generating process, the issue becomes even worse. And I have two very strong quotes here. The first from Kalut and Longo, who say, the more data we have, the more arbitrary, meaningless, and useless for future action correlations will be found in them. So big data is actually a curse, because you will find so many correlations, but you do not know which ones are the ones that are meaningful to you, right? You can actually mathematically prove this statement. You can show as the sample size or the number of variables becomes larger and larger, the number of meaningful correlations tends to zero, okay? And then there's another a nice quote by Popular. With data, enough computing power and statistical algorithms, patterns will be found. But are these patterns of any interest? Not many of them will be, as spurious patterns vastly outnumber the meaningful ones, right? And the question is, how do we pick among those correlations if we pursue our analysis without theory, without a qualitative background knowledge about the data generating process. So I believe, given all these issues and other issues, it's certainly not clear what can be learned from a pure theory-agnostic application of AI and machine learning. It might work very well for predictive purposes, and here these methods outperform traditional statistical methods, there's no doubt about this. But I believe in education research, we're interested in meaningful causal explanations and understanding. But here, AI and machine learning alone will be certainly insufficient. Maybe it changes in the future, we will see. So for a better interpretable AI and machine learning-based inference, I would propose to integrate AI and machine learning with traditional methods of model-based inference at all stages of the knowledge-generating process, and we should try to be very explicit about it, how theory and our research questions informs the choice of specific AI and machine learning methods and the corresponding tuning parameters. Okay. In any case, the limitations and assumptions, I only mentioned a few of them, of the AI and ML methods, you need to understand them so that they can use them responsibly, the tools, and you need to take them serious. For instance, if you have a small data set, there might be no need to use machine learning. You can do much better with traditional methods, right? Only if you have huge data sets where you or we as humans can no longer do it on our own, then it makes sense to think about AI and machine learning. So my claim would be that we should combine both AI and machine learning, but have a strong impact still of theory and research questions on all the choices we make through the entire knowledge generating process. Okay, now let me give you for about 15 minutes an example. In causal inference, that's my field of expertise, and I will use here a hypothetical study with no data, no formulas, with an observational data set. It's not a randomized experiment, so we introduce deliberately confounding issues here. So this is actually an example from psychology more than education. It's about the evaluation of the impact of online cognitive behavior therapy on depression. Right? So the treatment contrast would be between an online CBT intervention and in-person CBT intervention, and the expectation would be that the online version does as well, at least as the in-person CBT. Right? The outcome would be the Beck depression score. The target population would be college students with depression symptoms. And we have a couple of observed, or a larger number of observed variables and measures like depression measures, the cognitive affective mechanism, which are the brain activities that are highly related to depression, and you obtain some measures by using brain scans, different types of machines you can use like fMRIs. Then we have sociodemographic variables, medication substance use, and we also have measures on physical health. So these will be observed variables. But now we don't have a randomized experiment. Instead, the clinical psychologists conducting the studies, they deliberately assigned the students either to the online or the in-person CBT based on some observed measures. They might have looked at the measures of the cognitive affective mechanism, the depression score, and some sociodemographic variables, and then kind of deliberately assigned them. Maybe those with higher depression symptoms, they more likely put them into in the person CBT, and those with weaker depression symptoms more likely in the online CBT version here. And the goal here is to estimate the average causal effect. And the question is, can it be inferred from observational data where there's presumably selection bias or confounding bias in there? And then the question is, can automatized theory-agnostic AI and machine learning achieve the very same goal? Right? And the claim here is cannot. So just to an overview, I will only focus on one aspect because one could talk a couple of hours about the different steps here. But theory and research question and also AI and ML are involved at all the steps of the knowledge generating process. It starts with the design of the CBT versions, right? There's lots of theory involved. Then the measurement of the depression construct also is theory-based, right? We have careful measurement models here. The same holds for the cognitive affective mechanism. So we get the brain images, then you can use AI and machine learning tools to denoise the pictures, extract the certain areas in the brain that relate to depression, and so on. Right? And also when we select the objects and process the data, we do noise filtering, we do classification, labeling, and so on, which could be done by machine learning. I will only focus on the last part here, which is about the specification of the data model, particularly covariate selection, which means which covariates do we need to select to remove the entire confounding bias such that my effect estimates later warrants a causal interpretation. That's the goal here. So we have a causal research hypothesis, and that drives every single step in my analysis. I'm not doing a correlation analysis because I would not know which covariates to include. I have a clear goal. I want to separate the causal associations I'm interested in from the non-causal, the confounding associations. If I succeed in doing so, I will identify and estimate a causal effect, right? So this is certainly a challenging task. Why is it challenging? Because, as Pearl and McKenzie say, data are profoundly dumb about causal relationships. Why is this so? Because data only contain correlation association. There's zero causal information in the data per se. So where does the causal input, the causal information come from? It has to come from theory. In this context, particularly from qualitative background knowledge about how the data were generated, how the students got assigned into a treatment control condition, what are the causal determinants of the outcome, right? So we need to provide this needed causal input, which is of qualitative nature. Unfortunately, we can actually formalize, mathematically, rigorously formalize this qualitative information in a causal graph, also called directed acyclic graph. Once I have the causal graph, covariate selection is automatized. Okay, I will show you. So here I draw first the graph, right? So here's the causal effect of interest. I'm interested in the effect of the CBT versions on the depression score, which is fully mediated via the cognitive affective mechanism, the brain activities. And neuroscientists believe there's no direct effect, everything goes via brain processes, so there's no direct error. That's the causal effect of interest, okay? We're not interested in median effect because we don't have a direct measure of the cognitive affective mechanism. Then we might talk to the clinical psychologists in order to figure out how did they assign their students to the different treatment control conditions. And we might learn using qualitative methods that they looked at the measures of the cognitive affective mechanism at the pretest, that they also used the depression score, and they looked at a couple of sociodemographic variables. So we learn what caused an assignment to the treatment control condition. Next, we do literature review, right? And we might talk to the experts about depression, what they think the causal effects are, and then we might learn that there are genetic variants involved. Of course, we don't have them measured, right? But we draw theory here, we do not draw data, right? We might learn about that physical health plays an important role, that the cognitive affective mechanism, sociodemographic measures, and medication and substance use, right? So I draw this here. And now we need to think about how all these variables are causally interrelated. You see, you need lots of qualitative information in order to make a reliable selection of covariates. So once you do the task, you get a wonderful causal graph. And of course, that's not a matter of an afternoon. That's a matter of talking to the expert and doing lots of qualitative information. And one of my students, Nathan Quimper, and I just put out a paper that gives you step-by-step instructions how to draw the graph. Because it's actually quite challenging to draw a meaningful graph for practice. However, once we have the graph, when we put all our qualitative background knowledge into a formalized graph, that's now a mathematical object, covariate selection for causal inference is automatized. So we can use algorithmatized, so it's the same, so we can use a program package like the Getty, And that determines us whether the observed data we have are sufficient to identify the effect. And if so, it tells us which covariate sets will do the trick and remove all the confounding association. All right? Remember, no goodness of fit is involved. Covariate selection is purely driven by qualitative information. Okay? In our case, so we only need 3 sets of covariates, so measures of the cognitive effective mechanism, the pretest and sociodemographic variables, but it turns out that you could also use all other baseline covariates as well. It gives you all possible sets, not only one, right? Okay. So this guarantees us that our model will be substantively adequate. It meets the causal assumptions to remove all the confounding bias, and it clearly defines what the causal effect of interest is. So we are perfectly aligned with my research question and also with the requirement to remove all the confounding bias to warrant later causal interpretation. Okay, so now we talk about estimation. I know which covariates to use. Now I use the selected set of covariates and might do traditional regression or some propensity score methods, or why not machine learning? In this case, I would use double-D biased machine learning using the lasso. I'm not telling you anything about the technical details here. It's quite sophisticated methods. But what I want to highlight is that double-D biased machine learning works only if the sample size is large enough, meaning thousands of observations. If the number of variables is large and they meet the approximate sparsity assumption, most people do not even check these assumptions. And if the approximate sparsity assumption is not met, you get terrible results. Then you need to choose the appropriate variant of the lasso, like the double lasso. And then you need to use in addition a doubly robust core function. And then you need to still make sure that there's flexible enough model specifications in there, otherwise you might get misleading results. Then you need to do cross-validation in order to get rid of some regularization bias here. So only if all these conditions are met, then it makes sense to use double-D biased machine learning. If not, then you might stick maybe with the more traditional methods. So that's what my student Movon Kwan, he is today here, and I'm working on it and want to show some how these methods work in comparison to the more traditional approaches. Okay, so a next step, given all these uncertainties, it's still important not to combine it with traditional statistics, and that's what people are not doing in practice right now. You can still do for the treatment selection model balancing tests and plots, and for the outcome model residual diagnostics, right? You want to make sure that they are statistically adequate, that homoscedasticity is met, that independence is met, that the error structure is correlated, specified. And you do this by residual diagnostics. Okay? So only if substantive and statistical adequacy holds for the models, then a causal interpretation of the CBT effect is warranted, and statistical inference in form of confidence intervals or null hypothesis significance testing makes sense. Okay, just to summarize here the integrative aspects of the procedure. First, my claim is if we would not pre-select the covariates, you run at risk that the covariates you put into your machine learning approach will fail to identify a causal effect. Only when you integrate AI and machine learning with theory at all stages of the knowledge generating process, then a causal interpretation and inference is justified, and you actually understand what you got here and actually how to use it. Then you are more confident to intervene in the real work because you're more confident that it actually will work. But we are not talking about additional issues here like generalizability, which of course is still a major concern. So the integrative aspects here were that I formalized the qualitative background knowledge about the data generating process in using a causal graph that allowed me then to use an automatized algorithmic approach to select the covariates. Not goodness of fit, like machine learning would do, right? Remember, saying excellent goodness of fit is neither necessary nor sufficient. Then we use double-D biased machine learning with careful considerations of its requirement and in alignment with the causal research question we had here. And all the choices need to be informed by my goal of doing causal inference. All right? And finally, we used model misspecification in testing to establish statistical adequacy, such that we get then valid inference about a causal effect. Okay, so I have two final slides here. First, model-agnostic AI and machine learning emphasizes prediction and correlation-driven decision-making, and it's good on its own. When prediction is the goal you have, then go for it. But it's often devoid of statistical adequacy for inferential purposes and substantive adequacy for causal explanation and understanding. I hope I also convinced you that AI and machine learning depends on many substantive and technical requirements that are often not met in practice. Particularly, we never have infinitely large data sets, and if you only have, let's say, 1,000 or 2,000, it might not be large enough. Then the automatically processed data may not necessarily present the evidence you would like to have. So, of course, we use the data that are available for convenience, and we don't have the budget to collect new data. So it's natural to use it, but carefully reflect on it, whether the data really represent the evidence that is needed. If not, how it affects your conclusions. Then the AI and ML models typically fail to represent the phenomena of interest, particularly if you're interested in causal inference. You might have confounded correlations in that do not warrant a causal explanation and understanding. So I also like to think of AI and ML as system imitation rather than system identification, right? And we in education research would be mostly interested in identifying, understanding system processes that generate educational outcomes. And that's a quote by Karkaski and Mouly I used here. And finally, I would always say use AI and machine learning whenever appropriate, but explicitly guided by a theory and the research question, and then combine it with theory-driven and model-based methods when you analyze the data, and try very hard to establish statistical and substantive adequacy that allows then for causal understanding and explanation. But again, when you use the model-based methods, make sure that you really need to take causal and statistical assumptions serious. You need to understand the assumptions, you need to take them serious, and then you need to defend them. You need to show that the assumptions are met. Right? And I would claim only then theory and scientific methods will not become obsolete. Otherwise, AI and ML will certainly overtake. Thank you very much.